My name is Ananthakrishnan. I'm a PhD scholar from Department of Mechanical Engineering at IIT Delhi. So I do this problem solving session as part of my PMRF TA duty. So in this week, we'll see a few theoretical questions and numerical questions based on internal turbulent flow, which is a continuation of the examples that we have seen in the previous week. This is the first problem. Look into it. So it's a internal tight flow and turbulent case. So a stream of air with a Prandtl number of 0.72 is heated in fully developed flow through a pipe of diameter D fixed and uniform heat flux Q W that is QW. That's a fixed value. Since the Reynolds number RED happens to be equal to 2500, there is some uncertainty with regard to the flow regime that prevails in the airstream. Calculate the relative change experienced by the local temperature TW minus TM as the flow regime switches from laminar to turbulent. Look into it, and I'll also try to solve within a couple of minutes. It's a straightforward problem. So in this case, we need to actually calculate the relative change experienced by the local temperature TW minus TM. So it's a uniform heat flux problem, but the TW minus TM will vary with respect to the length of the domain. So even if it is laminar, then if it is a constant heat flux problem, so what you can say is that Q wall is equal to a heat transfer coefficient multiplied by delta T. So if it is a laminar problem, Nusselt number is a constant, therefore heat transfer coefficient will be a constant, and TW minus TM will be a constant throughout. The laminar section will be having the same TW minus TM. But as we move into the turbulent section, there will be a sudden change in the TW minus TM value. So the heat flux is kept a constant. The H value will be high, and then in that case, TW minus TM might go down. It's not straightforward. It actually depends upon a few Reynolds number parametric parameterization, and and we can determine that the general form and from the Reynolds number parameterization, and then we can substitute the value of the transition Reynolds number to calculate the actual ratio between TW minus TM. So straightforward intuition says that because the heat flux is kept constant, it increases for turbulent flow compared to laminar flow, TW minus TM should be less. So the ratio between TW minus TM between the turbulent and the laminar cases must be less than 1. So that is a check that we can employ in after finding the solution. We can employ this particular check to ensure that our solution is right. So what we could see is that we can approach the problem in such a way. We actually need to find the ratio between TW minus TM. So before that, I'll just draw what happens. So this is a laminar case, and there is a sudden transition to the there will be a transition, and then it will move to the fully turbulent flow. So this is a transition case, laminar and turbulent. So for flow within the tube, 2300 can be without any surface features or disruptions. 2300 is taken to be the transition Reynolds number. So in this case, the Reynolds number is 2500, and assume that this is well over the laminar range. It can be transition or the turbulent. So we have to calculate TW minus TM turbulent divided by TW minus TM of laminar. So this is equal to is the inverse of the heat flux. So basically heat flux heat flux by the heat transfer coefficient. So heat flux can be written as H wall minus T wall minus T main. So in this case, TW minus TM will be QW dash divided by HW. So this will be QW dash divided by HW for turbulent divided by QW dash divided by HW of laminar. So it will be the inverse of this ratio will be the inverse of the heat transfer coefficient, not the heat flux. I beg your pardon. So it will be H wall laminar divided by H wall turbulent. So this is straightforward. So the laminar heat transfer coefficient is less than that of the turbulent heat transfer coefficient, and because of that, this ratio will be less than 1. Now we use the we actually convert this heat transfer coefficient in terms of Nusselt number, so that we can directly use the standard correlations that are experimentally or empirically determined or analytically determined as well. So in this case, the Nusselt number can represent the HW in terms of the Nusselt number. It is equal to the Nusselt number in case of laminar multiplied by K divided by characteristic length. So in this case, it is a diameter. Similarly, for the turbulent, it will be Nusselt H turbulent will be equal to Nusselt number into K by D. So K by D remains a constant throughout, so it just get cancelled. So basically, the heat transfer coefficient ratio will be equal to the Nusselt number ratio as well. So we know that it is a constant wall heat flux case. So for the constant wall heat flux, heating case, so the Nusselt number is equal to 4.364. It's a constant for circular duct laminar flow for the laminar case. For the turbulent case, for constant wall or constant heat flux case, constant wall heat flux or constant temperature wall temperature case, the Nusselt number can be written as 0.023. Reynolds number raised to 0.8 and Prandtl number raised to 0.4 for the heating case. So substituting these values, you'll get the ratio as therefore we can get the ratio as 4.364 divided by 0.023 into Reynolds number D raised to 0.8, Prandtl number raised to 0.4. Prandtl number is given as 0.72. So this will actually reduce to 216.4, Reynolds number raised to minus 0.8. So the ratio of TW minus TM turbulent divided by TW minus TM laminar is equal to this value 216 Reynolds number with respect to the diameter raised to minus 0.8. Substitute the value of for RE equal to RED equal to 2500. This value will become equal to 500 is to minus 0.8 equal to some approximately equal to 0.414. So that substantiates, that validates our initial assumption that the ratio of the wall temperature minus the mean fluid temperature or bulk temperature in the case of turbulent to the laminar will be less than 1. So so for this Reynolds number, we could see that it is 0.414 at the transition. Now we can move to the second problem. Now this is also a numerical problem. Look into it. Water flows at the rate of 0.5 kilogram per second through a 10-meter long pipe with an inside diameter of 2 centimeters. It is heated. It is being heated with uniform wall heat flux at the rate of 5 into 10 power 4 watt per meter squared. Evaluate the properties at 20 degrees Celsius. Assume that the flow and the temperature fields are fully developed and calculate first the pressure drop over the entire pipeline. B, the heat transfer coefficient based on Colburn analogy, the heat transfer coefficient based on the Dittus-Boelter correlation, the difference between the wall temperature and the local mean water temperature, and finally the temperature increase experienced by the mean water temperature in the longitudinal direction from the inlet to export. So it's a straightforward problem. It's a uniform wall heat flux, actually simplifying quite a lot of assumptions that might appear if it was a constant wall temperature. And we need to calculate, if you know the friction factor, we can directly calculate the pressure drop. Then the heat transfer coefficient, these are smooth pipes, it doesn't have roughness. So that simplifies the problem to an extent. Then we need to calculate the heat transfer coefficient based on two analogies and one correlation. Then the difference between wall temperature and the local mean temperature, that is the previous case we have seen the same thing. Then the temperature increase experienced by the mean water temperature in the longitudinal direction from inlet to outlet. That's a variation. Try to solve it. I'll also try to solve it within a couple of minutes. So we can try to solve this problem. So the first part of the problem says we need to identify the pressure drop. For that, we need to calculate the friction factor. And we can use a correlation that is valid for a turbulent flow. So for that, we know that this is a turbulent flow problem because we are taking in the turbulent section. But how will we determine that whether the flow is turbulent or not? Through Reynolds number. So it is a tube pipe problem. So it's a flow through the pipe, and in that case, the Reynolds number should be less than 2300 for the laminar case. Much beyond that, it will be the so much beyond that, it will be turbulent, a transition then turbulent. So the water properties need to be evaluated at 20 degrees Celsius. So we'll find that from a property table. The thermal conductivity at 20 degrees Celsius for water, K is equal to 0.59 watt per meter Kelvin. Prandtl number is equal to 7.07. Density is 998 kilogram per meter cube. And then Cp is 4.182 kilojoule per kilogram Kelvin. And the kinematic viscosity is 0.01004 centimeter squared second. So if it is meter squared, it will be into 10 power minus 1. And first, we need to find a friction factor. So for that, we need to calculate the Reynolds number with respect to D. Characteristic length will be the diameter of the pipe. Reynolds number is equal to UD divided by mu kinematic viscosity. For that, you need to calculate the average velocity U. We know the value of D, that is the pipe diameter, that is equal to 2 centimeters. And mu will be the given value 0.01004 centimeters per second. So if we calculate the value of u in centimeter per second, substitute that. For so the u average value of u will be equal to the mass flow rate divided by rho into cross-sectional area. So the mass flow rate is 0.5 kilogram per second. Rho is 998. Area is pi by 4 diameter squared. So let's get the value of u is equal to 1.595 meter per second. Plug it in the previous equation. So it will be 159.4 centimeter per second multiplied by 2 divided by 0.1004. So the value of the Reynolds number will be equal to, from this it will be equal to 31,773, which is greater than 2,300, and the flow is turbulent. So we have to use a turbulent friction factor correlation. So as you could see, the friction factor for the duct flow, and this is the Reynolds number. Initially, this is the fanning friction factor. So for the laminar section till 2300, it will follow a linear variation. This is given by 16 by Reynolds number. And from beyond that particular point, there will be a sudden, at the transition, there will be a sudden jump in the friction factor because of the turbulent flow. The friction factor increases, but the friction factor actually reduces with increase in the turbulent flow. So at higher friction factors, at higher Reynolds number, the friction factor in the case of turbulent reduces, just like the laminar case. This is for the smooth pipe. And this solution is called, this solution determined by a relation from experiments conducted by Carman and Corazzi. Carman Nicorazzi relation. This plot is based on that. So once this is for smooth pipe, as and when the roughness increases, the friction factor also increases, and it will be parallel to that of the smooth pipe in a vertical direction. This is roughness. Roughness increases in this direction. Okay, then we have to use an empirical correlation for the smooth pipe. Can be Blaisier's solution that was present earlier, but we need to take care of the Reynolds number range that we are considering in this case. For smooth pipes, so we can directly plug in the equation. For smooth pipes, an empirical correlation, empirical an empirical correlation for friction factor in the case of turbulent flow is the final friction factor is equal to 0.046 Reynolds number D raised to -1/4. Note the minus sign on the exponent. So this shows that it's an inverse relationship. And this is applicable for Reynolds number between 20,000 and 10 power 6. So we can directly use it because our Reynolds number is 31,000. So the X validity is okay. And using this, calculate the friction factor in this case. The friction factor is equal to 0.046. The Reynolds number is equal to 31,000. And 1,773. Raised to -1/5. So the value of the friction factor will be 0.00579. So the higher Reynolds number, the value of the friction number of friction factor reduces, but it doesn't mean that the friction reduces because actual friction will be dependent upon the friction factor, the velocity, and density. So velocity is high in this case, and because of that, the actual friction might be high as well. So we know the value of the friction factor. Now we calculate the pressure drop. So the pressure drop equation will be equal to just the same equation as we have used in the case of the laminar flow. So this will be pressure drop divided by half rho u infinity. Here in the case of u mean squared will be equal to the friction coefficient CFX. No, this there is a small correction. So this comes from some other equation. Oops. So I'll try to explain how we'll get it. So we know that the skin friction coefficient could be written as the shear stress divided by half rho u infinity squared. then how could we represent the value of how can we represent the value of the shear stress? How can we represent the value of the shear stress from the in this equation to the pressure drop? So normally in the Hagen-Poiseuille flow, we have already got a pressure difference. So everything can be combined together. So in the case of a flow through a pipe, in the case of laminar flow, what we have written is that delta P could be written as the sorry shear stress could be written as delta P into D divided by delta P into R by 2 divided by L. So we can write the shear stress can be written as delta P into R by 2 divided by L. So this is based on the energy balance. This is based on the this is based on the force balance that can be conducted on a control volume. So in the case of a ducted flow, we take a small control volume. The shear stress acting on the bottom and the top part of the control volume will be balanced by the pressure that happens between the pressure flow drop that occurs between the starting and the end. So the shear stress multiplied by 2 times the surface area on which it acts. That will be 2 pi r into L on the outer and inner side will be equal to the pressure drop into pi by 4. Sorry. Uh, uh, this could be written as 2 pi r dr. So what we can do is that we can integrate it with respect to the 2 pi rl term will get cancelled out on both the sides, but then dr only thing that remains is tau into 2l is equal to delta p. 2 pi gets cancelled out. Integral of dr from 0 to outer r. So that will be r. Therefore, what we can write is as delta P is equal to V for the time being neglect the sign difference because shear stress will be acting in an opposite direction to that of the pressure drop. Pressure drop if this is the direction, and that means the flow is in this direction. So shear stress will be acting in the opposite direction. So for the time being, we are neglecting the pressure drop. So what we could see is that delta P into R by 2 L is equal to shear stress. So in the Hagen-Poiseuille, we know the value of delta P. We can actually find it from the fanning friction factor as well. So we know that the skin friction coefficient will be equal to shear stress divided by half rho u infinity squared. So using the skin friction coefficient that we have seen, we will calculate it as well. So this is one equation. So therefore delta P can be written as tau into 2L divided by R, and then substituting the value of shear stress, that will be equal to friction factor into half rho u infinity squared, half into rho u mean squared multiplied by 2L by R. Substituting that we will get the value of the delta P. Delta P is equal to F into half rho u mean squared multiplied by 2L by R. The friction factor will be 0.0579 multiplied by half into rho will be 998, u will be equal to 1.595 squared, 2 times 0.01 will be the radius, L will be equal to 10 meters. It's given in the problem. So the pressure drop across its length will be given as 14, somewhere around 690 Newton per meter square. So that completes the first part of the problem. Now we move into the second part. We have to actually determine the heat transfer coefficient based on the Colburn analogy that equates between the Standard number, Prandtl number, and the friction factor. So Standard number is an alternative way in which we can calculate the Nusselt number or the heat transfer coefficient. So option, so using Colburn analogy, we have to determine determine the heat transfer coefficient. So we can write the Standard number. So, Colburn analogy actually equates between the Standard number and the friction factor. So Standard number actually is kind of a relationship between the heat transfer coefficient and the amount of energy that is uh, stored in a fluid. So it is a dimensionless number that equates between the heat transfer to a fluid, that is actually measured by the heat transfer coefficient, to the heat store, that is actually measured in terms of the density as well as the specific heat of the specific thermal capacity. So that is rho Cp, in terms of rho Cp. mass flow rate into Cp, I beg your pardon. So it divided by the area, and we will get the value of rho v into Cp. So we can actually see into it. So standard number is a dimensionless quantity that relates the heat transfer to the fluid to the thermal capacity of the same fluid. So the Colburn analogy equates between the standard number and the Prandtl number. Standard number, Prandtl number, as well as the friction factor. Prandtl number is actually the ratio between the momentum diffusivity to thermal diffusivity. So effectively, it is kind of the bridge. The Prandtl number is the kind of the bridge between the standard number and friction factor. So momentum diffusivity is something that is equated to the friction factor, and the thermal diffusivity is actually the term of the Prandtl number that is equated to the standard number part. So what we could see is that standard number into Prandtl number raised to 2 by 3 is equal to friction factor by 2. Finding friction factor by 2. Standard number term is the dimensional quantity that creates heat transfer to the thermal capacity of the fluid. Prandtl number, momentum diffusivity divided by thermal diffusivity, friction factor. So standard number, we can write it as the heat transfer coefficient into area basically divided by m dot Cp into m dot into Cp. And then we divide the m dot Cp divided by area, then we can write it as rho into velocity into Cp. Into Prandtl number is equal to mu by alpha. We need not write it. We can actually calculate the Prandtl number. That's a property of the fluid at the temperature. So Prandtl number raised to 2 by 3 is equal to friction factor by 2. And from this, the only unknown is the heat transfer coefficient, and we can get it because it's difficult to calculate the heat transfer coefficient at each and every location. So what we do is that if you calculate the shear stress, you calculate the you back calculate to get the finding friction factor. And using this analogy, you calculate the heat transfer coefficients. That is one easy method in which we can calculate the heat transfer coefficient. So heat transfer coefficient is equal to rho UCP into F by 2 into Prandtl number raised to 2 by 3. So Prandtl number 2 by 3 will be at the bottom. You substitute the values straight away. And we'll get heat transfer coefficient based on the Chilton-Colburn analogy. Colburn analogy. Colburn analogy equal to F rho UCP divided by 2 Prandtl number raised to 2 by 3. We substitute the value. The friction factor in this case is equal to 0.00579. Therefore, H is equal to F rho U Cp F rho U Cp divided by 2 Prandtl number raised to 2 by 3. F is 0.00579. Rho is 998. U is 1.595. Cp is 4.182 divided by 2 into 7.07 the whole power 2 by 3. So the value will be equal to 7.86 into 10 power minus 4. 7.86 into 10 power minus 4, that will be, I beg your pardon, so slight correction. That is the value of the standard number. So we didn't actually calculate the standard number straight away. We calculated the heat transfer coefficient straight away using the analogy. So the value of heat, this will actually solve to give the value of the heat transfer coefficient. So that will come around this is 4.182 power 10 power 3. And this will be coming somewhere around 5,230 watt per meter squared Kelvin. So that will be the heat transfer coefficient. So we didn't actually experimentally determine the heat transfer coefficient. We calculated the friction factor using the shear stress or the pressure drop, and using that we calculate using this Goldberg analogy we calculate the heat standard number, and from that we calculate the heat transfer coefficient. Well, now we need to check whether this heat transfer coefficient is the same as that of we get using the Dittus-Boelter correlation. So our Reynolds number is very much greater than 10,000. From Dittus-Boelter correlation, is equal to Nusselt number P divided by L. So the Nusselt number value with respect to D will be equal to 0.023, Reynolds number raised to 4 by 5, Prandtl number raised to 0.4 for the heating case, multiplied by K by L. Substituting the value. So straight away, Reynolds number is 31,773. The whole power 4 by 5. Prandtl number is 7.07. The whole power 0.4. K is the value of K is 0.59 and diameter is 0.02. We'll get the value as 5930 watt per meter square, which is in the ballpark of the heat transfer coefficient that we have obtained from the Goldberg analogy. The heat transfer coefficient that we have obtained from the for Goldberg analogy is 12% lower than that of the Dittus-Boelter correlation. Now we can move to the third part of the problem. We need to the fourth part of the problem, we need to calculate the difference between the wall temperature and the local mean temperature. So that's straightforward. Just the continuation of the previous problem. So TW minus TM is equal to the heat flux divided by the heat transfer coefficient. And for this case, we use the Dittes-Boulder correlation for further analysis. The Dittes-Boulder correlation, the applicability of the Dittes-Boulder correlation will be for the Reynolds number greater than 10,000. There was a slight correction. So I mentioned that the Reynolds number should be less than 10,000. No, the Dittes-Boulder correlation applicability is for Reynolds number greater than 10,000. So for this case, the Reynolds number should be greater than 10,000. Then only we can apply the Dittes-Boulder correlation. So if that is the case, then our Reynolds number is greater than 31,000, and this Dittes-Boulder correlation is kind of accurate for our analysis. So please ignore what I have mentioned in the previous point. So this is correct. So the accurate value is from the Dittes-Boulder correlation. And the Prandtl number range will be 0.7 less than Prandtl number less than 120. That actually is correct in this case. Our Prandtl number is 7.07. So the Dittes-Boulder correlation is the accurate correlation for this particular Reynolds number operation. So this is based on the Dittes-Boulder correlation. So I can clearly note it down on the side. Applicability of Dittes-Boulder correlation. So for Reynolds number greater than 10,000 and Prandtl number of the range 0.7 less than Prandtl number less than 120. So this is the range of applicability of Dittes-Boulder correlation. Here it will be accurate. So the accurate value of the heat transfer coefficient is something that we can obtain using this Dittes-Boulder correlation. It's a general correlation that that will work with higher accuracy for this range of Reynolds number. So we can calculate the value of the temperature difference. Heat flux is given in the problem. It is 5 into 10 power 4. Heat transfer coefficient is 5930, and you'll get the temperature difference is 8.43 degrees Celsius. And the last part of the problem, we need to calculate the temperature increase in the longitudinal direction. The temperature variation in the longitudinal direction of the fluid. So that is dTm T out minus T in. So based on the energy balance, we can actually determine it. M dot into Cp into dTm is equal to the heat flux into the pi into diameter into dx. So that is dTm by dx is equal to q wall by d divided by m dot Cp, that is 5 into 10 power 4 into pi into diameter 0.02 divided by 0.5 into 4186. So that will be dTm by dx. This is equal to 1.5. Therefore, dTm by dx can be written as it's a linear variation in the case of constant heat flux. T out minus T in minus T in is equal to 1.5 into dx. That is the length of the plate. That is 10. That will be equal to 15 degrees Celsius. So that is an increase in the temperature in the longitudinal direction of the fluid. So that completes our second problem. So in this case, we have this was a long problem. This is a turbulent case. We first validated our assumption that this is a turbulent flow by calculating the Reynolds number, and it was above 30,000. It's above 2,300 definitely. Then we calculated the friction pressure drop. For that, we needed the friction factor. For this turbulent case, we used an appropriate correlation for the Reynolds number range. 20,000 to 10 power 6. We can use this correlation for friction factor. You could also use the Nicker-Ratze correlation also. Or you could superimpose it from the graph as well. And then there is other correlation provided by Blasius that it is also applicable in the range till 80,000. Then we using this normal Hagen-Poiseuille equation, you can substitute the friction factor and calculate the pressure drop. So how we got the pressure drop? We using this from this friction drop, from this pressure drop, we could actually calculate the shear stress and back and forth using this correlation of the force balance of a control volume within the duct. So delta P is equal to F into half into rho U mean squared into 2L by R, and we'll get a value of the pressure drop. So this is basically 14,690 Pascal. And the second part, using this friction factor, you have to calculate the heat transfer coefficient based on Kolban analogy. So the Kolban analogy tries to equate between the standard number, Prandtl number, and the friction factor like this. And from the friction factor, we can directly calculate the heat transfer coefficient, which should be a ballpark value compared to an accurate correlation. So the accuracy of the correlation is determined by the range of applicability of Reynolds number. So in our case, the Reynolds number is very much greater than 10,000, it's 31,000 around. So we can use the Dittus-Volta correlation. So while solving initially, I mentioned that the Reynolds number is less than applicability for Reynolds number is less than 10,000. That is wrong. The applicability of the Dittus-Volta correlation is for a Reynolds number greater than 10,000. So this is a perfect valid condition, and we'll get the accurate value of the heat transfer coefficient, and we plug in to calculate the temperature difference across the wall to mean temperature that we have seen the first question. And then finally, we determine the value of the temperature increment of the fluid through an energy balance of the heat of the control volumes starting from the initial to the outside of the fluid. So if we consider a pipe, this is the T in, T out, and this is the heat transfer. So heat transfer is equal to heat transfer coefficient, heat flux multiplied by the surface area, that is pi d into total length. That will be equal to the energy transferred to the fluid within the control volume. So m dot Ct into dT. And from that, we can calculate the increment in the temperature. That is 15 degrees Celsius. Look into the third problem. This is for the case of turbulence and the dimensionless wall variable. Tap water of 20 degrees Celsius flows through a straight pipe 1 centimeter in diameter with a mean velocity of 1 meter per second. Verify that the flow regime is turbulent and calculate the friction factor for fully developed flow. If the dimensionless thickness of the viscous layer of the constant shear stress region of the flow is equal to y plus equal to 11.6, what is the actual thickness y of the viscous sublayer? So viscous sublayer is 11.6. The dimensionless wall value of 11.6 is the region where the viscous stress are dominant compared to the turbulent stress. The viscous forces are dominant over the turbulent forces. So in that region, it will be inertial forces that will be balanced by the viscous forces. But beyond that, the turbulent eddy viscosity dominates over the viscosity term, the kinematic viscosity term. So we need to calculate the actual value of the y. Straightforward problem, you can do it and try to solve it. I'll also try to solve it with the topics. In this problem, we need to actually calculate the actual thickness Y of the viscous sublayer. Here, the given information are U is equal to 1 meter per second. Then D is equal to 1 centimeters. Kinematic viscosity is 0.01 centimeter square per second at water temperature of 20 degrees Celsius. And then Y plus value is given as 11.6. So the Y plus could be written as Y plus is equal to the wall dimensionless wall thickness. Y plus is equal to Y into shear velocity U star divided by kinematic viscosity mu. So Y could be written as this can be written as shear stress divided by density divided by mu. So in order to calculate the value of Y, you require the shear stress, density, and mu. Therefore, Y could be written as Y plus into mu divided by shear stress divided by rho. For is given in this problem, it is turbulent flow, and we need to calculate the friction factor for fully developed flow. So what we can write is a shear stress is equal to F into half rho U squared. So substituting the value F into half rho U squared divided by rho, cut. So you get Y plus mu divided by U root of F by 2. So we need to calculate the value of the friction factor. In the previous question, we have used the value of the friction factor using this correlation because the Reynolds number was greater than 20,000. So, but in this case, we do not know what is the value of Reynolds number, and whether we and we also do not know whether we can directly apply the correlation straight away. So first of all, we need to calculate the value of the Reynolds number. So it is UD divided by mu. U is equal to 1. Diameter is 1 centimeters. So it will be 0.01 divided by the kinematic viscosity is 0.01 centimeter squared. So that will be 0.01 into 10 power minus 4. So that will be equal to 10 power 4. The previous correlations was applicability was for the range of Reynolds number between 20,000 to greater than 20,000. So we do not know whether we can apply that. But there is a standard correlation of the so in this case we could use the correlation proposed by Blasius for Reynolds number less than 80,000. What we could use that we can use the Blasius equation given by 0.079 into 10 power 4, the whole power minus 1 by 4. So this is Blasius equation for finding F till 80,000. So this will be 10 raised to, this will be 10, that will be the value of 0.07. So it will be 10 power minus 1, it will be 0.0079. This will be 0.0079. That will be the value of friction factors. Back substituting that, we can calculate the value of Y straight away. That will be 11.6. Kinematic viscosity will be 0.01 into 10 power minus 4 divided by U. Velocity is 1 root of 0.0079 divided by 2. The value will be equal to 0.18 mm. So this value of the So this value of Y is the actual wall thickness. This value of Y will be the actual wall thickness uh, till where the actual viscous sublayer extends. So viscous sublayer will occupy a lower portion, a smaller portion of the total turbulent boundary layer. So this Y equal to 0.18 mm is the thickness of the actual thickness of the sublayer. So dimensions wall coefficient is 11.6, and this one is the actual wall thickness of the viscous sublayer. It takes into consideration the shear velocity, and which is dependent upon the shear stress. So the shear stress is a function of friction factor and the velocities. The local friction factor F is given by this correlation Blasius equation, and and that is dependent upon the Reynolds number, local Reynolds number. So we know the value of the local Reynolds number since it is a turbulent flow and it is within the duct, the Reynolds number U into D remains a constant. So in this case, the mean velocity is 1. That will be the constant throughout. So that we can assume that the UD divided by mu and the corresponding friction factor remains a constant throughout for the section. And if that is the case, then the viscous sublayer thickness also remain a constant. Since this is not a free stream, not a flow or a flat flow. This is an internal duct flow. So the maximum the boundary layer thickness can go is uh, the maximum the boundary layer thickness can go is the half of the diameter. That is a radius. And because of that, this remain a constant in a fully developed in a fully turbulent flow, and therefore the viscous sublayer also remain a constant. So in this case, for this velocity, shear stress, shear velocity, and we can get the value of the viscous sublayer as 0.18. Look into the fourth problem. So this is a reverse calculation to of the first problem. or the second last problem of the second last section of the second problem as well. So here water is being heated in a straight pipe with an insert diameter of 2.5. The wall heat flux is given as 10 power 4, and the flow under temperature fills the fully developed. It's a fully developed flow. The local difference between the wall temperature and mean temperature of the stream is 4 degrees Celsius. We need to calculate the mass flow rate of the water stream and verify that the flow is turbulent. We need to evaluate the properties of water at 20 degrees Celsius. Look into it. I'll also try to solve it with the net developments. So we can try to attempt this problem. It's a straightforward problem. We need to calculate the mass flow rate. For that we need to use some kind of correlations to get the heat transfer coefficient, and from that for the Nusselt number. We know this is a turbulent case, so the Nusselt number can be equated to the heat transfer coefficient. Uh, if you get the value of Nusselt number, you can try to get the value of the Reynolds number, and then from the Reynolds number of velocity, and then calculate to get the mass flow rate. So that can be an approach by taking an assumption that the flow is turbulent. But so we assume that that flow is turbulent and then back calculate the velocity. That should be the approach in this problem. So it's a straightforward one. At 20 degrees Celsius, we calculate the water property. The conductivity is 0.59, the same thing that we have been repeating. Mu is 0.01004 centimeters squared per second. Prandtl number is 7.07. Density is 0.998 gram per centimeter cube. The heat flux is given, so we calculate the heat transfer coefficient straight away. QW divided by delta T. So in this case, the temperature difference is given as 4. Heat flux is 10 power 4. Straight away, we can calculate 2500 watt per meter squared Kelvin. Nusselt number is Hd divided by K. So it's 2500 into diameter is 2.5 centimeters divided by K. K is thermal conductivity 0.59. We'll get the value of Nusselt number straight away. So then we need to equate it to the, assuming this is turbulent flow and the Reynolds number is very much greater than 10,000, we can assume, we can use Littus-Coulter correlation straight away. It's an assumption, and we need to validate it by using the actual value of Reynolds number that we can get after by calculating the Reynolds number. So we can say that Nusselt number is equal to 0.023, Prandtl number raised to 0.4, Reynolds number raised to 4.5. So that will be equal to 105.93 equal to 0.023. Prandtl number is 7.07.4 and Reynolds number raised to 4/5. Therefore, Reynolds number is equal to substituting, finding the value of Reynolds number from this equation. Reynolds number will be equal to 14,270. U is equal to, from this we can calculate the value of U. UD divided by nu is Reynolds number. So basically Reynolds number nu divided by D. So 14,270 multiplied by kinematic viscosity, that is 0.01004 into 10 to minus 4 divided by 0.025 will be equal to the value of velocity, that is equal to 0.573 meter per second. So since the Reynolds number is greater than 14,270, the assumption of turbulent flow and the use of Dittus-Coulter correlation are right. So we can get the value of the U, and from there we can calculate the mass flow rate, that will be equal to rho UD divided by rho UD, we given rho into U into pi by 4 into D squared. So basically it's area, velocity term, and the mass and the density. So rho is 0.998 gram per centimeter cube. U is 57.3 centimeter per second. Pi by 4 diameter is 2.5 square. So this will give the value in terms of gram. So that is equal to 281 gram per second. That is equal to 0.281 kilogram per second. Bit more logically. So that's also a problem. So it was a straightforward problem to back calculate the mass flow rate from the heat flux as well as the temperature difference is given. So we calculate the heat transfer coefficient. From there we back calculated the Nusselt number, and from the Nusselt number we back calculated the Reynolds number by using an assumption that the Reynolds number, the assumed Reynolds number is greater than 10,000, so that the applicability of Dittus-Coulter correlation and the turbulent flow is valid. And the Reynolds number that we got was in fact greater than 10,000. So the applicability of the Dittus-Coulter correlation is valid, as well as a turbulent flow is also valid. So then from the Reynolds number, we back calculated the velocity, and from the velocity, we calculated the mass flow rate. So that's a straightforward problem, just a mathematical manipulation. Look into the fifth problem. So a flat sheet tabular iceberg drifts over the ocean as it is driven by the wind that blows over the top. So that makes it clear that this is not a case of internal turbulent flow. It's a case of turbulent flow over a flat plate kind of a problem. The temperature of the surrounding seawater is 10 degrees Celsius beneath the iceberg, and the relative velocity between it and the iceberg is 10 centimeter per second. So the iceberg floats beneath the water at 10 centimeter per second. The length of the iceberg in the direction is of the in the direction of the drift is L. Calculate the corresponding mean velocity when the atmospheric temperature is 40 degrees Celsius. Basically, it's a heat transfer problem. It's the iceberg floats over the iceberg kind of floats over the water. So if you want to picturize it, so this is an iceberg, this is water, and this is air. The iceberg is freely floating. It's drifts. So iceberg is drifting over the water. So that is freely floating. So in that case, the net force acting on it will be equal to 0. Kind of an inertia. That means that the shear stress that the force that acts, suppose it drifts in this direction. The shear stress due to the water flow. The relative velocity between the iceberg and the water is 10 centimeter per second. So the shear stress in this direction will be shear stress in water into the area on bottom surface. Force exerted by the wind. Wind will be expected to flow in this direction. So if it is supposed to push this iceberg, then the wind velocity will be greater than that of the iceberg in this direction. There will be a relative velocity in this direction. So the corresponding wind velocity From these shear stresses, we can calculate the velocity differences. But the drag forces is actually shear stress into area on bottom and top. The shear stress can be expressed in terms of friction factor. And for that, we require the friction factor for the flow over a flat plate in the case of turbulent flow. We do not know till now whether this is flow is a turbulent or a laminar case, but we assume that the flow is turbulent because we are putting this in the turbulent case. And what we do is that we try to calculate the value of shear stress, the average shear stress. We try to derive that equation. So shear stress is given as half into rho u infinity squared into CF, local shear stress. The average shear stress can be denoted by O bar. So this CFX, if you get, you can calculate the value of the shear stress, and the average shear stress is equal to half rho u infinity square and CF x integral of 0 to L dx divided by L. So that will be the average shear stress. So in this case, we have to use the average shear stress, but for that we need to calculate the local shear stress first. But we are not going to do that. We'll use the equation. But before that, I'll explain how we can use how we can derive these correlations. Flow over a flat plate and turbulent flow, not a duct flow. So I'll give a brief overview how to get this value. So we know the integral momentum equation for the pressure difference in the x direction equal to 0, since it's a flat plate kind of a problem. So we get d by d, so to infinity mu dy equal to 0 divided by. This is the case of a turbulent flow. That's why we are using the mean velocity. There is a fluctuating term also. We are ignoring that while calculating the value of all other average quantities. So it's a straightforward problem. What we try to do is that we have got this one equation. We actually need the value of tau 0 by rho, but we do not know the u bar velocities. Then we use a velocity profile. In this case, it's a power law, 1/7 power law. So what we do is that uh, so we use u plus is equal to u bar by u star uh, is a function of y plus. So y plus could be written as we have seen the value y plus is y into the dimensionless wall distance variable y plus could be written as uh, 11.6 mu divided by u star. So we have already seen in the previous case, the y plus value is equal to 11.6, and from that we can get the value of y. So y plus is equal to basically uh, y into the u star divided by mu. So y plus could be written as y into u star divided by mu. So what we could write is that u plus is a function of y plus, and we use a power law 1/7 power law curve fit Prandtl's 1/7 power law. In that case, what we could write is as if of u is 8.7, this f could be written as 8.7 into y plus the whole power 1/7. So if is a function of y plus, so exactly if you write using the Prandtl's 1/7 law, you can use f of u if u is equal to 8.7 y plus raised to 1/7. So u bar divided by u star could be written in terms of this one. Uh, so basically it can be written as the previous equation says that if u is equal to 8.7 uh, y plus raised to 1/7. So u plus, that is u bar divided by u star is equal to 8.7 y plus raised to 1/7. So that is the equation. So at y is equal to delta, this will become equal to u bar will be equal to u infinity. So that will be uh, this can be written as second equation. Then u infinity divided by u star is equal to same 8.7. Y plus will be equal to y into u star divided by mu. So y will become equal to delta u star will become u star divided by mu, the whole power 1/7. So this is one boundary condition. So at u infinity, and that equals u infinity and delta. So basically, we have this equation u bar is equal to u infinity minus u, and we substitute u bar as u star into 8.7 y plus raised to 1/7, where y plus is given by y into u star divided by mu, and we integrate y from 0 to infinity, and we only need to do it from 0 to delta, and substitute the value of u infinity in terms of substitute the value of uh, u infinity by u star in terms of delta. We'll get the value of the integral equation in terms of delta, and the right hand side is our shear stress. shear stress term, and then we can obtain the value, everything in terms of a shear delta. So this is to substituting 2 in 1 and using boundary condition 3, we'll get shear stress divided by rho infinity squared is equal to 0.0225 u infinity delta divided by nu raised to -1/4. And from this, what we can get is so this is actually a relationship between the shear stress and the value of delta. And shear stress, you know the velocity profile, and we just the velocity profile is u infinity by u star. U bar by u star is equal to 8.7 y plus raised to 1/7. And this could be written as u star divided by u star is equal to 8.7 delta u star divided by nu raised to 1/7. So that we have using the shear stress value. Now now what we do is that we calculate the value in terms of x. If we can write delta in terms of x, that will be better. So what we could do, we know that shear stress varies with respect to delta, and shear stress varies with respect to x, and delta varies with respect to x. Ultimately, both are a variable of x. So we know the velocity profile, and we substitute, we differentiate at x equal to 0, and obtain the value of, and use and then substitute it in this equation, and we'll get the value of delta. So we know u infinity by u star is equal to 8.7 delta u star divided by nu. Now to calculate shear stress, that will be equal to mu dou u by dou y at y equal to 0. U velocity profile is equal to u bar divided by u star 8.7 y plus raised 1/7. We take the derivative, and we get delta by x equal to 0.37 u infinity x divided by nu the whole power -1/4. That is that is that is just like what we have done for the laminar case. We can get it for the turbulent boundary layer thickness as well. So using these two equations, we can calculate delta, substitute the value of delta here, and we can write the tau 0 in terms of only x. So basically, we know the value of delta straight away, and we can actually kind of get the delta from here itself. So u infinity u. This is another equation that corresponds to u star and the delta. So what we could write is that u star can be written as root of tau rho divided by u. So you substitute the value of tau rho here, and you can get the value of delta in terms of x. So using these two equations, we can calculate the shear stress divided by rho u infinity squared is equal to half CFX is equal to 0.0296 u infinity x divided by nu raised to -1/4, and the average value of the shear stress rho u infinity squared average 0 to x is written as half into CFX 0 to x 0.037 u infinity x divided by mu raised to -1 by. So that gives the value of shear stress. So then coming back to our problem, force of drag force on due to wind on ice is equal to drag force on water on ice, that will be shear stress average into area top equal to shear stress average water into area. So top surface wind and bottom water cancel using the shear stress formula 0.037 u infinity x divided by mu the whole power -1 by 5 to the 0.037 u infinity x divided by mu on the wind and on the water side. Multiplied by there is this rho u infinity square term as well. So rho u infinity square term and rho u infinity square term on the water side as well. And this is the wind side. Basically rho varies on both the sides. U air and the U wind and the U water are different. The other parameters x and nu is also kind of different. So we actually club the terms that we want. We want u infinity air divided by u infinity water, that is a relative velocity itself, it's -1 by 4, and rho uh, you take the power of 5, it will be 10 minus 1, it will be 9, and then rho will be the kinematic viscosity will be scaled by the power of 1 by 9, while the density will be scaled by 5 by 9. So it will be equal to rho water divided by rho air, the whole power 5 by 9. Basically, we uh, take the power of 5, so rho 5, and then take the power by 1 by 9, so it will be 5 by 9. And here it will be mu water divided by mu air, mu wind. So air is same as wind here. So that will be 1 by 9. Substituting the values, you get the ratio is equal to 32.4. And from U water is equal to 10. Therefore, U air is equal to 3. This is 10 centimeter per second U water. Given 10 centimeter per second, so that is 0.1 meter per second, 0.1 meter per second. Therefore, the U air equal to 3.24 meter per second. So that completes the problem. It's a straightforward problem. Taking the total force acting on the system equal to 0. That means the shear stress on the top multiplied by the area on the top will be equal to shear stress on the bottom divided by 8 into area. Because it is assumed to be freely floating. That means that net force will be equal to 0. The only force that is pushing it will be the force that is acting on the backside of the iceberg. If you assume that there is no backside for iceberg, it's a continuous body, then in that case you take that it is freely floating. In that case, the net force will be equal to 0. So the air will be at a higher velocity, therefore the shear stress on the bottom will be counteracting in a direction shear stress to the bottom. Though the shear stress on the top side is actually pushing the iceberg, the in the forward direction, it will be acted in an opposite direction by the fluid at the bottom that will be at a lower velocity. It's a case of relative velocities. And the same can be seen in the case of a boundary layer formation, where the top layer will be near towards the center, will be in the case of a duct towards the center will be at a higher velocity, while the as we move away from the center, that will be at a low velocity, and a fluid control volume in between will be experiencing uh, forward thrust, just like the air is pushing the iceberg in the forward direction, while the bottom water will be slightly at a lower velocity, and it will be pushing it backwards. Because of that, the net force is equal to, we could see that both these net forces gets cancelled out each other. And it continues to be in a state of free floating because of the initial motion it had. For that, we require the shear stress equation. Shear stress can be obtained from the for the flow or a flat plate in the case of turbulent flow using Prandtl's 1/7 the power law. Using the momentum integral equation, we substitute the Prandtl's 1/7 the power law velocity equation, and then we can get a relationship between the shear stress and the delta, that is a boundary layer thickness. And then we can substitute this then we can actually get the value of delta. We can have a relationship between delta and x, and then we substitute that. We can get the value of shear stress in terms of shear stress and the x. And using these two, we can actually finalize a equation for shear stress and then substitute it straight away. So the shear stress equation is of the form of average shear stress is of the form of this one, and we substitute and get the value of the velocities. That completes the set of problems for this week. We have seen a few numerical problems based on internal duct flow and one final problem based on the flow over a flat plate turbulent case. I hope you understood. We'll meet next week with the final week's lectures. Till then, it's bye.